So let's talk about function call stacks and a related concept called stack frames. Now, we have seen how custom functions, or in fact any kinds of functions in C, work. When we call a function, control passes from one function to another function. When that happens, or in order for that to happen, it is necessary to maintain a data structure called a function called stack. Now, what is a stack? Uh, Generally in English, you can think of stack as a pile of something. Now, imagine, for example, you have some plates, like a bunch of dishes. If you have many of them, you'll stack them up one on top of the other. And generally, you add new ones on top, and if you need to remove one, you'll remove the topmost one again. This kind of arrangement, this type of data structure, is called a stack, and it uses what's called a last in, first out mechanism to add or remove elements from it. The act of adding a new item onto a stack in programming is called pushing an item onto the stack. Removing an item from it is called popping an item. We will be doing something similar in order to enable us to use functions. The function call stack is sometimes also called the program execution stack. We'll stick with function call stack. It's simply a simpler term. The function call stack, among other things, keeps track of once we call a certain function and jump to a different part in the program, it keeps track of where we have to go back to continue execution of the program. In addition to that, it also maintains the different variables that exist within different functions, local variables. Now, remember that when you call one function, that called function can in turn call another function, and that function can then call yet another function. But as the last function called completes execution and either returns a value or not, it must return control back to the function that called it. And that is basic. That is the thing that the function call stack keeps track of. What we call the return address, the place in the calling function where we need to jump back to after the execution of a called function ends. Each time a function is called, a new entry, kind of a new item, is pushed onto the stack. Each of these items is called a stack frame. And the stack frame contains, most importantly, the return address to which control has to be returned after the function finishes execution. But it can also contain other items such as local variables of the function that is currently executing, also called automatic variables. But if before finishing execution, the called function calls another function, yet another stack frame is pushed on top of the function call stack. Now, if this is becoming slightly overwhelming, don't worry. I'll show you a graphical representation linked to an example that we've done a little earlier to explain how this works. At the top of each stack frame is always the return address. Everything else is underneath that. So, like I said, besides the return address, other things contained in a stack frame are the variables, the local variables of a function, which include also the parameters of a function. Remember, when you call a function, all the parameters are created as local variables of the called function. Those are also stored, contained in that function's stack frame. A function's stack frame exists only as long as that function is active. Like I said, once it completes execution, that stack frame is popped from the from the function call stack and disappears. And with it, all the values of its local variables are also lost or forgotten. Now, like I mentioned, a function can call another function, and before it finishes execution can call yet another function, and that one can call yet another function, which means the size of the function call stack will grow with each function that is called by the next function, which means that the amount of memory needed to store the function call stack increases as successive functions call other functions. Eventually, since a computer's memory is finite, eventually what could happen is that your system may run out of memory. If that happens, this is a fatal error, and it's called a stack overflow. Remember that term. So let's consider an example. So let's say our system, our computer, is initially just running the operating system, and from within the operating system, we call a program's main function. We start a program, we run a program. Now, the place in the OS where we were when we called our program, let's say that the address of that location is R1. That address needs to be remembered and needs to go into a stack frame onto the function call stack. Let's consider this example. This is a slight modification of the first example that we used to learn about custom functions in C. This is the one in which we created this function square, which returned the squared value of the integer argument it received, and therefore returned an integer as return type. On line 6 over here, we have the function prototype, and we have a slight modification. Like I said, in the main function of this program, we only define an integer a and initialize it to 10, and then we have a printf statement over here that takes two arguments, the value a, the variable a, and the return value from the function square when a is the argument, and it basically prints out a squared and then whatever the value of square of whatever the value that function square returns. Let's see how this execution would happen in terms of the function call stack. So initially, main gets called from the OS from some location R1, and execution of the program begins in main. Integer variable a is defined, and then comes the printf statement, and inside of that the program calls the square function. So now we have two calls. The call to square adds another stack frame onto the function call stack, or pushes another stack frame onto the function call stack. And this second stack frame will contain the address R2, from which the call to function square went out. If you want to visualize that, it looks kind of something like this. So you start off in the OS. At some point in the OS, when we were at some point in the OS, we began execution of our program, began with the main function. When we do that, this stack frame over here is pushed onto the function call stack, and it contains at the top the return location that we have to go back to from where in the code of the OS, from at which we were when we began execution of this program, the main function. Now in the main function, we are also defining integer variable a, and that will also be part of the stack frame for the main function. Following that, when we reach the printf statement, we call the square function, and that takes us to function square. When we do that, another stack frame is pushed on top of the function call stack. At the very top of that will be the return location R2, representing this place here in the code, to which we have to return after we complete execution of function square. Also remember that function square takes as argument x over here, a parameter that creates a local variable x, and that's what we see over here. That is part of the stack frame, of the second stack frame that we just pushed onto the function call stack. Now after square executes and calculates x times x square, it needs to get back to the main function, and since x times x will be returned to function main, the variable x that was created as part of square function's stack frame, that is also no longer needed. So as control returns to the main function, the stack frame, the last stack frame that we added for square onto the function call stack, is popped, meaning all of this is removed, and we jump back to this location that we had kept in here, and that takes us back to function main. And this will be the situation after that. So we return from square back to location R2 in the main function, and the function call stack now contains only the stack frame for function main. The main function will eventually also finish executing and return. And it'll return to this location R1, this line, this instruction in the operating system. And when that happens, this stack frame will also be popped. So this is basically what happens behind the scenes when we call a function. And related to that is this standard C library that from which we have been using functions, also called headers.h files. So I want to show you some of the most significant header files that are part of this C standard library. You can, of course, also create your own libraries. Let's say you write some interesting code, useful code that can be reused. You can organize those functions into groups, and you can group those function prototypes into your own .h extension header files. If you do that, so we've already used the hash include preprocessor directive to include header files from the C standard library. And when we do that, we usually use these angular brackets for stuff like stdio.h. So we use these angular brackets when we're including header files from the C standard library. But if you want to include your own custom-made header files, we use these double quotes instead. So let's say the square function, you like it very much, you think you might reuse it, you find it very useful, that's fine. You'll have to create for that a corresponding header file which contains squares function prototype, and you could in the future include it in other programs without rewriting the code by putting this line at the top in your program together with the other preprocessor directives to include other header files. And here are some of the most significant ones, and we've already seen some of these. There's limits, which we used in one example, that contains the sizes of various data types and limits, numbers like that. We have math.h, of course. We use the power function, sine, cosine, tangent functions, etc. Those are all in here. Similar to limits.h, size limits related to floating point data types are contained in float.h. Then, of course, there's standard IO, which we've been using since the very first example. And we'll be using stdlib very soon when we look at random number generation. We'll also be using string.h, which contains many functions that can be used to work with strings, with text.